Hello students, welcome to our YouTube channel Experience Tutor. Today we'll discuss class 12 physics, get more than 95% marks, electromagnetic induction, chapter 6, ncert line by line, part 3. Before we start today's lesson, we again have a humble request. Please subscribe our channel if you have not done so. Please like and share our videos among your friends and relatives so that they can also get benefited. Please click on the bell icon so that you should not miss any of our videos because you will get automatic notification whenever a new video is uploaded by us. Then let us start today's lesson. Today we'll start with the section 6.6 Motional Electromotive Force. Let us consider a straight conductor moving in a uniform and time independent magnetic field. Figure 6.10 shows a rectangular conductor PQRS in which conductor PQ is free to move. So here in this figure, PQ is free to move and with a velocity v in this direction, and L is the length of the RS, which is same as that of PQ as given in the figure, because uh, they are parallel to SP and RQ are parallel to each other, and PQRS forms a rectangle. Now the rod PQ is moved towards the left with a constant velocity v as shown in the figure. Assume that there is no loss of energy due to friction. PQRS forms a closed circuit enclosing an area that changes as PQ move. So what does this sentence means for now the PQ is here. As soon as PQ moves to this place, say this place, then what will happen? Its area. Now the area is this much. Area is this much. Initially the area was this much. So it is changing. The area is changing. And there is no loss. We are assuming there is no loss due to friction. It is placed in a uniform magnetic field B, which is perpendicular to the plane of the system of this system. So B is the uniform magnetic field. So B is the uniform magnetic field which is perpendicular to the plane of this system. If the length RQ is equal to S X and RS is equal to L. If RQ is equal to X, RQ is X and RS is L, it is given. The magnetic flux phi B enclosed by the loop PQRS will be phi B BLX. BLX. B is the uniform magnetic field and L is the length. This L is the length. Here, L is the length. This is L and X is the breadth. So phi B is equal to BLX. Since X is changing with time, the rate of change of flux phi B will induce an EMF given by. So since the PQ is moving this side, so X is changing with time. So rate of change of flux phi b will induced EMF, and that EMF will be equal to E is equal to minus d phi b by dt. Instead of phi b we can write BLX minus d BLX by dt is equal to minus b dx by dt. Why? Because b and l will be are constant, and it will come out, and only dx by dt is left. So instead of dx by dt, what we can write? We can write velocity, because dx is the distance, dt is the time. And since it is a direction is given, so it is a vector quantity, displacement and time, displacement about time, that is velocity. So blv we can write this. So hope this portion is clear, easy. Okay, let us move forward. Where we have used dx by dt is equal to minus v, which is the speed of the conductor pq. The induced EMF BLV is called motional EMF. The induced EMF BLV is called motional EMF. Thus, we are able to produce induced EMF by moving conductor instead of varying magnetic field. That is, by changing the magnetic flux enclosed by the circuit. It is also possible to explain the motional EMF expressed in equation 6.5 by invoking Lorentz force acting on a free charge carrying carriers of conductor PQ. Consider any arbitrary charge Q in the conductor PQ. When the rod moves with a speed v, the charge will also be moving with a speed v in the magnetic field B. The Lorentz force of this charge will is qvb in magnitude, and its direction is towards q. So remember, Lorentz force on this charge, Lorentz force on this charge is qvb. You have to remember this. We have done it in electrostatics and also in electricity chapter. And its direction is towards q. So let us see the figure again. So its direction, the charge direction will be this. When okay, all charges experience the same forces in the magnitude and direction irrespective of their position in the rod PQ. The work done in moving the charge from P to Q is work done is equal to work done normally is equal to force F dot S, or force into displacement. So force is how much? The Lorentz force, that is QVB. Displacement is how much? Displacement is L. So the work done is equal to QVBL. That is the work done. in moving that charge from P to Q. So W is equal to QVBL. Since EMF is the work done per unit charge, so what is EMF actually? EMF is equal to work done per unit charge. So W by Q, put the value of work done, QVBL upon Q, cancel it. So EMF will be equal to VBL. That is the EMF. This equation gives EMF induced across the rod PQ and is identical to equation 6.5. We stress that our presentation is not wholly rigorous, but it does help us to understand the basis of Faraday's law when the conductor is moving in a uniform and time dependent field, magnetic field. On other hand, it is not obvious how an EMF induced when a conductor is stationary and magnetic field is changing, a fact which Faraday verified by numerous experiments. In the case of stationary conductor, the force on its charge is given by. So, what is the force? So, F is equal to QE plus QVB. So, take Q as common. So, is equal to what is left here? E plus VB. So this is the force. Now, since V is equal to 0, one more thing. On the other hand, it is not obvious how the EMF is induced when a conductor is stationary and the magnetic field is changing, a fact which Faraday verified by numerous experiments. In case of a stationary conductor, the force on its charge is given by. Since V is equal to 0 by this equation, since V is equal to 0, why V is equal to 0? Because it is stationary. So this whole part is 0. So we are trying to find out how the EMF is induced when the conductor is stationary. That is V is equal to 0. So if V is equal to 0, this portion becomes 0. So what is left? Only this portion left, Q into E is left. So this is the force. Thus, any force on the charge must arise from electric field term E alone. Therefore, to explain the existence of induced EMF or induced current, we must assume that time varying magnetic field generates the electric field. So, time varying magnetic fields generates the electric field. That is the main important gist. However, we hasn't to add However, we hasten to add that electric field produced by static electric charges have properties different from those produced by time varying magnetic fields. So we also know that static electric field have different properties than time varying magnetic fields. In chapter 4, we learned that the charges in motion, that is current, can exert force or torque on a stationary magnet. Conversely, a bar magnet in motion, or more generally a changing magnetic field, can exert a force on a stationary charge. This is the fundamental significance of Faraday's discovery. Electricity and magnetism are related. So ultimately what they want to say that moving moving charge, when the charge is in motion, that is current, can exert force on a stationary magnet. So current electricity can exert force on a stationary magnet. On the other hand, we have also seen that moving or changing magnetic fields also exerts a force on a stationary charge. And this is the basic fundamental significance that Faraday has discovered that electricity and magnetism are related. So example 6.6, a metallic rod of 1 meter length is rotated with a frequency of 50 revolution per second. With one end hangs at the center and the other end at the circumference of the circular metallic ring of radius 1 meter about an axis passing through the center and perpendicular to the plane of the ring, that is figure 6.11. A constant and uniform magnetic field of 1 Tesla parallel to the axis is present everywhere. What is the EMF between the center and the magnetic ring? So this is the figure. Solution method 1. As the rod is rotated, so this is the rod, metallic rod, and it is rotated. As the rod is rotated, free electrons in the rod moves towards the outer end due to Lorentz force and gets distributed over the ring. Thus, the resulting separation of charge produced an EMF across the ends of the rod. At a certain value of EMF, there is no more flow of electrons and a steady current is and a steady state is reached. Equation 6.5, the magnitude of the EMF generating across the length dr of the rod as it moves right angle to the magnetic field is given by. So if we consider the rod, then we are telling that long electrons are distributed and um, distributed over the ring, thus resulting a separation of charge produced in the produced an EMF across the ends of the rod. Fine. At a certain value of EMF, there is no more flow of electron and a steady state is reached. So after some time, there is no flow of electron and a steady state is reached. So basically what happens? EMF. What is EMF? You have to understand electromotive force. So it is like a potential difference. So you think like a this. This is a tank which is full of electrons, and this is another tank which is electron is little less than that. So here full. So a pipe is connected here. Consider this. Imagine this. So what will happen? Electron will flow from here. So this is called potential, and the difference in potential is called potential difference, PD, and PD is called PD is the EMF. Potential difference is the EMF. So what will happen? Electron will start from flowing from 1 to 2. After that it flows. A time will come when the levels are equal. When the levels are equal. When the levels are equal, will there be any flow? Same as that of water. Will there be any flow? No. There will be no flow. So it is called steady state. So so steady state is reached. So in this case, we say that steady state is reached. So equation 6.5, the magnitude of the EMF generated across the length dr of the rod as it moves right angle to the magnetic field is given. dE is equal to bvdr. bvdr. Now we can write E is equal to integration of dE, that is integration of 0 to r bvdr. We integrate it, instead of dE we have put the value of bvdr. So we put the limits 0 to r, then v, instead of v, what we can write, v is equal to omega r. So we have put, instead of v we have put omega r here. Now put the integration to dr, integration, definite integration 0 to r, 0 to r. If we solve, then r by r square by 2 it will come. So b omega, so integration of r dr will be equal to, and 0 to r will be equal to r square by omega. Just it is a simple law of simple integration problem. So ultimately we get this. B omega was initially there, and r dr's integration 0 to r will get r square by 2. Note that we have v is equal to omega r, it is already given. So EMF is equal to half 1 to 2 pi 50 into L square, that is 157 volt. So just put the values, you will get this. In method second, second method also we can calculate. This is the first method, and second method what we'll do, to calculate the EMF, we imagine a closed loop OPQ in which O and P are connected with a resistor R, and OQ is rotating rod, is the rotating rod. The potential difference across the resistor is then equal to the induced EMF and equal to B into rate of change of area of the loop. That if theta is the angle between the rod the radius and the radius of the circle P at time t, the area of the sector OPQ will be given by pi r square theta upon 2 pi, which will be equal to r square theta upon 2. Why? Because pi will get cancelled with pi, where r is the radius of the circle. Hence the induced EMF is E is equal to B into d half r square theta by dt is equal to half b r square d theta by dt, and d theta by dt we can write omega. Why? Angular velocity, angular displacement upon time, that is angular velocity omega. So b omega r square by 2, and d theta by dt omega is equal to 2 pi nu. So omega is equal to again we can write 2 pi nu. Now this expression is identical to the expression obtained in method 1, and we get the same value of V. So this was the second method. Now the next example, example 6.7, a wheel with 10 metallic spokes, each 0.5 meter long, is rotated with a speed of 120 revolution per minute in a plane normal to the horizontal component of Earth's magnetic field HE at a place HE is equal to zero point 0.4 G at the place. What is induced EMF between the axle and the rim of the wheel? Note 1 G is equal to 10 to the power minus 4 Tesla. So induced EMF is equal to half omega B R square. So you remember this formula. Induced EMF is equal to half. We have derived this expression in the second method just before the sum. So put the values here for Omega you put 2 pi nu, and nu is zero point 0.4, and put all the values, and you will get the value of the induced EMF. The number of spokes is immaterial because EMF across the spokes is parallel. Remember this point. And let us keep today's class till here. Before ending today's session, we request you to subscribe our channel if you have not done yet. Please like and share our videos among your friends and relatives so that they can also get benefited of that. And please click on the bell icon so that you will not miss any of our important videos, because it will you will get an automatic notification whenever a new video is uploaded. Thank you very much for your support and watching our videos. Thank you.